Okay, this talk is about recent developments in satellite navigation and a new field of military endeavors that's called navigation warfare. The talk is first a short introduction on how satellite navigation works, what their simple characteristics are, and goes on to some technical and political considerations regarding the possibilities to influence satellite navigation in various settings. I assume most of you are familiar with what GPS is and what satellite navigation is, and just repeating on the core points. Satellite navigation works, most systems work by having a precise atomic clock in a satellite, or a number of satellites, and having knowledge about what orbits these satellites are flying. The time from the atomic clock plus the orbit data are encoded into a fraction signal, a little bit later, what that is and what it means, and transmitted downward to Earth where it's received. From the signal, you can derive information at what time this signal has left the satellite and at what position the satellite was. So, from that data from several satellites, you can geometrically calculate the position on the surface of Earth in 3D. That means it's longitude, latitude, and altitude. Of course, the altitude is more or less an idealized altitude calibrated to sea level, but sea level is something that is not very constant in some areas. The decoding of the signal requires a key. It's something like a code that contains the sequence of the frequencies, possible spectrum, and time. If you look at what this is being used for or not for, is this. What we see here is a blunt direct attack ammunition. That's an plain old bomb that has a square bomb, which are the green parts. The blue part is the bomb. The green parts are the navigation payload. It's containing a GPS receiver and controls for the fins and at the end of the bomb. So what they're doing is strapping this stuff onto cheap bombs to make them GPS controllable. By using these fins, the bombs can navigate to a relatively precise position that is being programmed into the GPS receiver. So this is what navigation warfare is against. So if you're on the receiving end of that, you might be interested in how to jam GPS. Okay. For some sort of definition, what is navigation warfare? There are various definitions around this, is more or less the condensation of that. If you want to gain the ability to deny your enemy to know where he is, where you are, where his forces are, and you maybe want to introduce false information into the enemy's perception, saying, okay, rendering space out of a GPS reality. There was a very famous city map in Moscow that simply didn't contain a part of the city, a small part of the city, and they did it in a very ingenious way. If you look at the road map goodbye, there was a street going through that area straight. In reality, the street was splitting in the beginning of that area in left and right lane and making an elliptical figure around that area and joining behind it. So this area was rendered out. And the same thing can be achieved with GPS spoofing. It's a little bit difficulty, of course, but of course, what you all want to do is preventing your enemy from doing the same to you. If you're dependent on satellite navigation, then it's a bad thing if your enemy can deny your capability. If you look at the recent war in Iraq, the United States were heavily dependent on GPS. Not only the military version, but also civilian version. From the reports that came back from the field, what the GIs really used, there were astonishing reports. One thing was, they had a problem that friendly fire at the platoon level was deemed a real threat. That means that people are shooting each other because they didn't know behind what rock his body is. So what they were giving people, the soldiers, the little walkie-talkies was built in GPS that you could buy at a camera that had the capability to just, on the push of a button, transmit your position to all your bodies and receive your positions from all your bodies and display them on the device. So it's $200 more or less, depending on the kid's toy, but okay, it saved their lives again. So they were heavily dependent on GPS there. So there were rumors about Iraq having GPS jammers. Apparently they had some, but these were very true devices that were quickly destroyed for many months. But at least they tried. The warning sign was in the beginning of the campaign when they began to intensify their attacks against targets in the no-fly zone, so-called no-fly zone. You might remember it was right before the war. There was one day where they had attacks on communication centers. And the reports, the target reports were that the bombs were all about 60 meters off to the left, which is quite a significant event if you're bombing a target and you know, okay, bombs are falling in a random pattern around your target, but all 60 meters off to the left is a little bit too much. So they concluded that the Iraqis were using GPS jammers, and then came all the rumors that they had GPS jammers from the Russians bought and tried to use them. We come into technical details a little bit later. Preventing the enemy from jamming your satellite navigation is becoming more and more important for a lot of people, and so that's why a lot of nations are investing very heavily into satellite navigation stuff. I'm going a quick tour through the four main systems that are in operation today, or will be in operation very shortly, because it's very important to understand the politics behind this navigation warfare. The most used system and the most stable system today is the GPS system, formerly called NASDAR, which is the newest military system. It's also open to civilian use. It has a minimum capability of 24 active satellites. Currently there are 28 up. The orbit is around 20,000 kilometers. We have a 12-hour orbit period. 5 ground monitoring stations are monitoring the satellites, position of satellites, signal quality, all that kind of stuff. And there are 3 uplink stations that are transmitting this data back up to the satellites. Because, if you remember from introductory, the signal also contains all this information about where the satellite is. And since satellites in orbit are quite a tricky thing, you need to monitor them and put in correction information from orbit deviations, or if it has become a little bit slow from some kind of interference or whatever, you need to put in correction information. This correction information is being transmitted upward to the satellites by these uplink stations. There are roughly 2 modes of operation at the moment in the GPS system. With the course acquisition code, that's what you have in a civilian GPS system. That code is not very sophisticated. It's has about 1.423 MHz chirp rate, which means it changes the frequency at about 1 MHz rate. And the period of the code, which means is the public, the server code that is controlling the frequency copy, changes every millisecond. It's the rollover time. So this is quite a simple code. In comparison, the military system, just a step on it. The military system has a hugely longer code. It has a rollover time of 7 days. There are 2 frequencies, it's L1 and L2. The course acquisition civilian mode uses only L1. The military mode uses both frequencies. The advantage is that if you use both frequencies, you can compare the signals and have a higher resistance against jamming interference. I detail that a bit later. GLONASS is the Russian system. They had all planned to have 24 operating satellites and 3 orbit planes. Currently they have only 8 because of funding problems, and their satellites are dying because they are way beyond their planned lifetime. And operating such a system is quite costly. The beauty about the Russian system, from a technical perspective, is they are using laser tracking to track their satellite orbits. That means they have ground stations in Russia, and they're using lasers and laser reflectors on the satellites to track the satellite orbits and send out correct information. The system works basically the same as the GPS system. It has not as high precision in the standard, which is the civilian signal. The accuracy on the military signal is said to be around 30 meters, so it's also not as precise as GPS is. The civilian signal on GPS gives you about 10 meters accuracy and is said to go down to 1 meter and below for the military signal. The ground system is currently mostly used as a backup in receivers that have a high reliability. So where you need an application, you need high reliability, put in another GLONASS receiver just to have a bit of a backup. So it might not work all the time because the GLONASS satellites are failing, but sometimes it might settle up. So they're trying to revive the system, and they try to talk to Europeans into helping them into joining their system, the GLONASS system, but it didn't work out. So GLONASS is still on its own, and the chronic funding problems in Russia might make it a little bit difficult for them to keep the system up, but it's still undecided. Okay, then there's a little bit of a surprise. There's a Chinese system. The Chinese decided that they want to have a satellite navigation system because they wanted Taiwan back and all these issues, and where it might come handy to have something that is not dependent on the US. The Chinese system is not a global navigation system, but a regional positioning system. The reason is very simple. China has no need to make war in Kosovo or Afghanistan or somewhere else around the world, but they just want to have position accuracy around their area. And so they decided to build a regional positioning system, and the way to do it is not to put 24 satellites in orbit, but use 3 geosynchronous satellites. The technical details of the Chinese systems are still a little bit sketchy, so it's unknown what kind of receivers they use, what kind of modulation they use, and how huge the antennas on their geosynchronous satellites are. Just for reference, it's about twice as high the orbit as for the GPS satellites. So it will be interesting to get more data, but still a little sketchy. The Chinese are very interested in anything that has to do with space, and the reason again is Taiwan. Because they think that from a strategical viewpoint, that at one point they will need to go up against the US about Taiwan, or against any US supported power about oil in its purpose or whatever. So they know that if they want to go up against the US, they need a capability in space that is able to counter the US space capabilities. That means they need their own navigation system, they need their own communication satellites, they need their own signal satellites, and they need their own focus satellites. And they have all that. If you look at the Chinese space program at the moment, it's targeted at achieving space equality, at least in terms of features, not in terms of mass, in the next 10 years. So if you look at that program for coupling in spaceship, they had a civilian spaceship, that coupling is another civilian spaceship, and coupling ships in orbit is quite a technical challenge, and but there's a whole another interesting application of coupling ships in space, which is mines, putting explosive stuff near or at other people's satellites. which is a very fast and sure way to make sure that the US has, in case of trouble, and reduce all the capability. So everything that the Chinese do in space has always two factors. One is prestige, the second is space strategy in terms of military. So it's really worth watching, and the name of the system is Baidu. The Europeans discussed for, I think now since 1985, about having something similar to GPS. And the discussions went on and on and on and on. This is always the case in Brussels. And the system nearly died 2 years ago, but then the US took notice and began opposing the system. Really, really massively. And at some point in time, about 6 months ago, France and the German government said, yeah, we didn't understand the space issue fully, but if the US are so terribly against it, there must be something about it, so we should keep on. Okay, this was of course the simplified version. But in essence, that is the reason that why Galileo is now in progress, and the funding issues have been resolved, and the program management issues have been largely resolved. And there are still some sort of resistance from the US in the field of the frequency allocation panels, because Galileo will be very near or probably inside the frequency bands that the US is using for GPS, which is not a problem in itself because it's a spread spectrum, and it makes it very easy to design receivers that can receive both Galileo and GPS, which would be really, really useful, because then you don't have 24 satellites giving you precision, but 54 satellites or even more satellites giving you a precision signal, and you have faster precision times all that kind of stuff. So a receiver that integrates both GPS and Galileo would be really great for everything in satellite navigation. And the reason why the US is so thoroughly opposed against it is that they want to have navigation warfare capability. If they begin to reduce the accuracy of their signal, or if they introduce a regional jamming or modification of the signal, and there is a completely independent system run by the Europeans that they have no influence at all about, then they got trouble, because they can't deny the capability to an enemy. Like if they denied the GPS capability to the Iraqis, and the Iraqis could still use, or whatever the Iraqis are then in 10 years, could use the European system, yeah, that would be a problem for them. So the European society, there are two reasons why we want Galileo. One is being independent from the Americans, because you never know. And the second reason is, of course, economics. The satellite navigation is already a huge business, and is becoming even huger more and more, because the receivers are getting cheap, and there are a lot of useful applications for tracking assets around. Like there are folks around who want to track every container that they ship, every container. And there are hundreds, thousands, millions of containers being shipped every day. So they want to track cars and stuff like that. So that the rental cars being tracked by GPS is just the beginning. So the European, of course, want to pie the cake. And so the problem that they run is their own bureaucratic structure. They solve the problem more or less. And the technical design of Galileo is quite good. So they, from the beginning, designed in high resistance against jamming and spoofing. They designed in integrity monitoring. That means that you can see at your receiver if your signal is being spoofed or jammed or whatever. They have put in the second signal, which is called commercial signal. That signal costs money. If you want to subscribe to that signal, it costs you money, because it's a high precision signal and has an assured reliability. They say, okay, you get that signal if you have no obstacles to the sky in 99.5% compared to 97% reliability of GPS. This is quite a step. And the stated goal is that they want to build a system that can fly airplanes with. So this is what they want. They want to have the capability to reliably fly an airplane navigated by Galileo. Okay, so currently there's a debate around in the ITU about frequency allocation starting by ITU, that they are coming to an closure, like having a joint working group on that or whatever, so that they can go forward. The system will launch in 2008. The control of the system is civilian, so it will not be like in the US that military control, but it will be civilian control. And I'm really looking forward to the system of works out. Okay, so let's go down a little bit from politics to the technical issues. The signal, as said, is spectrum looks like this. You have on the upper axis with time, lower axis frequency. That means the signal is not using one frequency all the time, but is lumping through frequencies over the time. And it's putting in just a bit of useful signal at each blip that you see there. The jumps between a high design of frequency are controlled by a pseudo-random sequence. Pseudo-random sequence is it looks random, but is being derived from an algorithm or state machine. The beauty of the system is that it's hard to intercept if you don't know the jumping sequence, because you cannot guess at what frequency the next bit will show up. And since it's so short, if you just look at the signal in the spectrum analyzer, it looks like noise. So without knowledge of the point in space, and frequency and time where each frequency will be used, it's really difficult to intercept. It is possible if you monitor the signal for a while, and you can make a guess about the length of the pseudo-random sequence. Another beauty is that you get a sort of mathematical gain, because you can use a very big signal, and you can just, if you know at what frequency you need to listen at what point in time, you can detect your frequency much easier. So it's much more resistant against noise and things like that. So GPS was the first big system that used the spectrum, like we use a system of users, but today's spectrum is basically the standard, like it's used in wireless LAN and mobile phones and stuff like that. So it has become the standard mode of operation for radio systems for a while now. So, coming down to what could you do to deny your enemy the capability to know where he is. If you're a system owner, that means you're the owner of GPS and can control satellites, you can just switch off, always an option. You can introduce an artificial error by either manipulating the message that's being sent to the terminal, the receiver, about where the satellite is, because then the mathematics shifted it. Or you can introduce a little bit of dither in the time clock frequency signal. It means sending pauses out a little bit earlier, a little bit later will ruin your calculation where you are. This error introduction was used by the US called selective availability, which means that the civilian signal was degraded to, I think 100 or 300 meters, depending on very rare at what time. So 100 to 300 meters is quite a bit accuracy. They are more or less unusable for a lot of applications. So what they wanted to corner the market in satellite navigation, so the government decided, okay, let's get rid of this selective availability. It was Bill Clinton who finally made the decision, and get the signal to the market. But of course the military said, yeah, we want to have something that we can use against the potential enemy. So then this whole navigation warfare business came up. So what they're now doing is they're introducing a new block of satellites. The GPS satellites are numbered in blocks. Currently the satellites that are on orbit are block 2A and 2B. And the new satellites will be block 3. Block 3 is significant changes against the current system. There is higher transmission power, has the capability to locally jam or locally introduce errors into the system, like saying, okay, we want to have just over Iraq, and the the surrounding countries a signal that's not as good as it could be. And they want higher resistance against jamming. That means it's reducing the frequency, introducing new code sequences and stuff like that. So that's why they are currently building about 3 satellites and will launch them shortly in order to get the system more robust on one hand, and on the other hand to gain capability to reduce it on the regional level. Another option would of course be changing the codes. If you have, for instance, a problem that your military system seems to have been compromised, or the code seems to have been compromised, you can always change the code, but the problem is, of course, you have a lot of receivers in the field, there are millions of receivers, and to change the code with all of them requires substantial effort. Anybody like us or other evildoers. The easiest thing is jamming the signal. Jamming is come from general electronic warfare. That means like they are putting in enough energy into the radio band where the signal is to prevent the receiver from seeing the signal or interpreting the signal. Then the second method is spoofing a signal. It means changing it or replacing it with a manipulated signal. You can also retransmit a manipulated signal if you know how to do it and do it in the right time frame. Another option is to get really high precision. GPS services are often augmented by ground-based services. The term frequently uses differential GPS. What it means is you have a station on the ground that precisely knows where it is, and it's monitoring the GPS signal and is just transmitting the difference between what the GPS says where it is and because it knows where it is. So in this, there's a certain probability that this difference is also valid for the surrounding area. So if the GPS system says, okay, you're off 300 meters in that direction and 500 meters in that direction, then the differential station will send out these codes to the receivers and they can correct the signal. Differential GPS has come a little bit out of favor after selective availability was switched off because it was the tool to circumvent selective availability. But it's still around, especially if I can navigate, you can fool around with that. And the fifth option, of course, you can destroy receivers. If we go into jamming, the simplest way of jamming is continuous wave. You're just taking a frequency band where you think your signal is and putting in some noise. And the design of the noise and the design of the wave that you put in there is very important for the efficiency of the jammer. I found some Russian research that did actually test roughly and transmitted a seamless wave that was optimized to go through a lot of points in time and frequency where the GPS signal transmits bits. Did some fancy mathematics based on the characteristics of the GPS signal to design a seamless wave. And actually they ended up with a very, very simple jamming transmitter, only 10 you can find. And they found that if they transmit this just 1 milliwatt and had even some attenuation of that in the right band, they could jam GPS about 200 meters. It means that they calculated this stuff up and said, okay, if we have a 1 watt transmitter transmitting a signal on the right frequency, we could jam for 500 kilometers. The reason is that the GPS signal, when it comes from space, is incredibly weak. The current GPS transmission power in space is, I think, 600 watts. Usually when it go out with that 1000 watt. So it's really weak when it comes down to Earth. This kind of jammers is relatively easy to build. You can do a lot of more things if you want to raise your efficiency. There is this famous schematic published in Crack, where they have an Gaussian wave jammer, where they have Gaussian noise generator, putting the power into the right band. And you have also quite some impressive results in jamming GPS. the problem with their design is that it's not easy to build. It's not something that you can do if you have never had any contact with high frequency electronics. You need some kind of measurement tools and stuff like that, so it's not very easy to do. But in comparison, for an industrial enterprise that is used to build high frequency electronics, it's easy. So the Russian design is, I think, even simpler. There are boards around for continuous wave channels that are about that size, very simple stuff, and they are designed to be plugged with a 9-volt solar cell and transmit for an hour from a balloon. Just hook it up on a helium balloon, let it get up and drift into land, and GPS Galileo. And they make nothing much of power, so yeah, quite substantial reach. A much more interesting, from a technical point, interesting method of jamming is in opening jammer. It means in jammer that knows where the next bit of the signal that you want to jam is being transmitted. It concentrates his jamming energy there. And that requires that you know the pseudo-random number sequence that is driving the frequency down, so that you know where the next frequency is being used in that pattern. And that reduces your required output power substantially. The normal continuous wave jammer spreads the energy about all the band. If you look at the Russian split of 3 megahertz band, which is quite a wide band. Put in energy there, you waste a lot of power because you only need very few bits of frequency at a time. We concentrate on jamming power. So if you put the 1 watt jamming power precisely on the right frequency at the right time, following the operating sequence, you have much more efficient jamming can go with a much lower transmission power, which means that the probability that your enemy will find the jammer and destroy it is getting substantially lower. And if you can build a design, they have thousands of these small jamming devices just spread into the countryside, then your enemy is quite a problem. That's the reason why the PRM for the military signal is as secure. And it's totally secured by a combination of it's the civilian code and the new code that is being introduced to further encrypt the signal, so it's difficult to get into the signal. If you just compare the length of the code for the military signal and the civilian signal, you see that the military signal has about, I don't know what it is, trillions, more than 6 trillion jumps in the sequence in server random over the 7 days. 7 days in the rollover, then the sequence starts again. And the civilian code is just 1223 jumps, which is non-leasing, so that this is very easy to get. And the sequence rolls over. So if you want to build an hopping jammer that is following the military signal, you need to know the PRN, and that we are a little difficult even with today's techniques. There is of course an option to sum up the band, so that you're choking in the band that you want to monitor the computer and monitor for weeks and weeks and weeks, and just add up what you got in the band and hope that you find the sequence. So that's a little bit difficult because we huge amount of memory and really fast supercomputers, but probably too. City at home is something very similar. Spoofing is of course a more interesting option than jamming. The reason is that your enemy, if you do it right, will not know that this is reversing as a spoof. So you will trust his navigation, and you control the navigation system. That's absolutely perfect situation. But it's not as easy to achieve as jamming. There is one relatively simple option of spoofing the GPS signal. If you remember, the GPS coordinates are being calculated from the time of arrival at the receiver. So the GPS signal carries the information that has left the satellite and travels the 10,000 kilometers through space and atmosphere and arrives at the receiver. And from the minimal differences in time that the signal takes from the satellite in its normal position to the receiver, the position is being calculated. So if you can somehow interfere with the time when the signal arrives at the receiver, then you can manipulate position. And the way to do that is very well known in electronic warfare. It's called a delay line. This is being used, for instance, in anti-radar warfare, where you just get in the signal of the radar that is yelling at you, and sending out a little bit delayed the signal again, maybe it's from the power. So it means, in using the radar quotation, that you're looking a little bit behind where you are. So because the radar receiver thinks you are farther behind because the signal took longer to travel. You could do essentially the same thing with the GPS signal. Notice that you need a very, very short delay line, and you need transmit power very high, so that you have a strong signal that the GPS receiver will lock onto your signal, not onto the real signal from the satellite. And there are also some parameters that come later on that makes it a little more difficult, but that's an option. So that way you can spoof a military GPS signal without knowing the pico. So you just don't know anything about the signal, you just know what band it transmits, and you're retransmitting the signal. There's a lot of electronics issues and radio frequency issues involved in that, but there is substantial knowledge that such systems are on the market. The short code for the civilian system makes a fully synchronized copying jammer, means a jammer that is just synchronizing on the GPS and following the GPS sequence, or pre-guessing the GPS sequence and just putting the jamming energy there. Much more easier. So it's just 1023 jumps, so it just can be programmed into microcontroller where there is no significant obstacle. And it could be very easily used to suppress the original signal and introduce your own signal. You want to tell somebody that he's Australian or something like that. Again, spoofing is much more useful but much more difficult, but it's possible. So integrity monitoring is absolutely essential in your GPS system. If you see something spooky on your receiver electronic positions, like that, and you should check if you're a wealthy enough target that somebody should use a GPS spoof on you. Okay. Consideration for that spoofing engine. It's always desirable to have a high antenna position. If your antenna is on the ground, your enemy can use methods like just upward pointing antenna that only gets signal in from the satellite, not from this surrounding on the ground, which is the easiest way to do that. So if you have antenna on aircraft or balloons or whatever, you have a high probability of getting the signal through to your enemy. There are some rumors about possibilities to use satellites to send a signal, so that you can have a really huge area that is being switched off for navigational purposes, but this is only a rumor, so if you know the transmission conditions in your area, like there are reflections before, where signals are damped and stuff like that, it's also to advantage because you can model your emissions according to the propagation patterns in the area. And you should never forget your own dependency on the system. If your own forces are depending on the navigation system and you're jamming it, then okay, you might get a huge disadvantage. Okay, what is being done to protect against jamming spoofing? There are a huge number of special antenna designs being introduced now into the market, especially for high reliability receivers and military receivers. These antennas either just point up or are prehistoric antennas, or antennas that know where position of the object you're on. So if you're on a phased array antenna, model a reception pattern that's only very narrowly targeted to the satellites that you want to receive. That's being possible with phased array antennas now, and that is something that is very, very difficult to defeat. What US is doing using multiple codes that are being add on each other, scrambled with each other, so that's difficult to know where the sequence is now, and changing the pattern or kind of making it difficult to construct a hopping journal that is not looking onto the sequence. Introducing ground-based augmentation monitoring systems allows you to monitor GPS quality and tell your receivers in the area if the GPS quality is substantially deriving from the patterns that you expect. So if you see on your differential GPS station that you have astonishingly 50 kilometers deviation from the position that you are known that you are there, then something is fishy, that's obvious. Okay, you can put on more transmission power on the satellite. That's what everybody's doing at the moment. There are limits to that because power is a scarce resource in space. And of course, integrity checks at the receiver. It means the receiver tries to monitor the position and what kind of speed he expects to move. So if you're walking and then suddenly accelerate to 1,400 kilometers per hour, there is a clear assumption that you are not traveling as an F-16. So you might be in gentle school. So there's a lot of construction possibilities to know who are being spooked on them, but it's again difficult to produce. If you buy a new GPS receiver, then check it has at least some capabilities to show the quality of the GPS signal and do some technical check on that. Okay, that's from me so far. I would really love to hear questions and maybe some mistakes I made, errors I made. Yeah, thank you so much.
Yeah, just to let you know where I'm coming from. I spent the last 7 months sort of getting trashed by the international space community. I was at one of the conferences actually at San Diego, announced Galileo coming out. It seems to me that most of these systems are not really necessary for orienteering. You can sync your clock and find your position with good geodesy on the Earth with high precision without any satellites. It seems to be based on the psychological obsession of, to use the space for peace, finding the ultimate high ground for controlling everybody on the Earth, trapping everybody on the planet. And if you do want to leave the planet, according to these guys, you're going to go work on you're going to go be a slave on a mining colony on Mars, or you're going to be a slave on a mining colony on the Moon and help break it up. So, I really don't buy into it, and space could be a problem. It's only going to get worse. Galileo seems sort of like a sugar-coated version of GPS, It's the same companies, Boeing and Lockheed are behind it. And I was at the International Space University. Essentially, I was, the French government sort of helped me get back in there because I left and I saw what they were doing. It was so atrocious. I saw what they were doing 2 years ago, but, it's the same group of people, it's the Boeing, the Lockheed, and the US DOD. It's a sense that, the Operation Paperclip is a sensitive issue here, but it's the same stuff that's going on. It's nothing new. Hopefully space will go away and once people can, be free to explore the universe, but I think that's a long way out. And frankly, I'm worried people are going to be trapped on the planet, and the only way to be able to leave is to go to a slave line on Mars. It's ridiculous.
Yeah, of course. I try to keep my eye on things that are out here. So on that, just try to cover the situation at least on a technical legal level. The difference I think between GPS and Galileo is that the ultimate control of the system and the ultimate design goals of the system have been set not by generals, but by people who want to make money. And I'm not saying that it's better, it's just different. So that's,
well, those are the same people.
Huh?
They're the same people.
Yeah,
It's the same people. I met them. I was at the school and I saw what they were doing. Generals and the corporate leaders, same people.
okay.
There's no difference whatsoever.
Okay.
I wanted to know about the Garmin Cloud GPS. It's got a little connector for the computer. Comes through this. I wonder if you know about the Garmin 12 GPS I'm using for cruise tracking. The signal which comes out of it and goes into the computer. What's in that signal?
The signal that is coming out of commercial GPS receivers, it's in almost all cases NMEA compatible. NMEA, is the signal standard that is being, the transmission standard is being used and serialized to give you position, speed, velocity, and satellite status. And some other minor stuff. If you do some mathematics on what you get out of that, you can get a rough impression of how the satellite status is in your area. But the key to tracking for spoofing of jamming is that you track the signal over time. So you look for suspicious jumps, that you look for suspicious satellite disappearances and appearances that are not consumed with what you would expect from the system. And of course, this can be easily done with the computer coupled to the GPS. So that if you look at the current use of GPS, so the most useful thing that I do with my GPS besides navigating and driving around is geocaching, and which has done a lot to popularize GPS at all. And the whole concept of connecting the GPS to the computer has made this industry possible. It's all tracking and asset tracking stuff and people tracking stuff and so on. But if you look at the spy-shots catalogs, you can now buy small units that you can stick under a car that are tracking you via GPS and transmitting the stuff the LG is then going to build into that thing. And so there's plenty of reason to know that you can disable GPS capability in your surrounding if you need to.
If I'm not mistaken, your position is calculated from deviation in time that the satellite sends its data at the time the rise of the client. How does the client know what time it is?
It's encoded in the signal. The signal is a quite complex thing.
Yeah, but that's the time the signal was sent.
Huh? Yeah, you can do a differential operation over the signal to get the client synchronized in time before trying to navigate over time.
Hello? Yeah, I have a question. If you have a Galileo receiver, which doesn't have a direct view of the sky, maybe you get a signal which is bounced from a ball or some other things. Is the Galileo system better at detecting those things or in GPS?
The Galileo system, one of the design goals of the Galileo system was to enable better reception inside cities, which is always a problem with funny jumps of your GPS position to track the GPS position. While driving down the road, you always have these little jumps off the road and on the road, depending on what kind of building you have on the side of the road. And the Galileo system has a higher transmitting power, and the modulation code is much more resistant against reflections in the way that you can see better if the signal has been reflected or not. So you can put in better anti-reflection capability in the receiver. Plus, if you have a remote receiver that is doing both GPS and Galileo, you have a higher probability that you have at least some satellites aligned on the street so that you don't need reflected signals but get very, very good scan. But the reflection business is what gravity operators are trying to do in a city GPS navigation systems.
Would Galileo also be available indoors, where you don't have any direct satellite, or is it really total?
If you look at the transmission power and the frequency, that's 1.5 megahertz, it has not a very high penetration power. So you cannot expect to have indoor reception capabilities that are far beyond GPS. They might be a little bit better in the areas like, okay, if you're at a fairground or something like that, it might be competitive. It will not be a huge jump.
It sounds to me that if I'm at the receiving end of those bombs you showed, right?
Yeah.
Or if I'm likely to be in the near future, and if I know that, then for me it's relatively easy to at least find out if the area I'm living in, if there are any jamming attacks running, because what I could do is I could, in a safe time, set up a place where I have a GPS receiver, where I know where this place is, and then just monitor where the GPS receiver thinks it is, right? And if I see my position jumping, which is in fact not changing, then I know something fishy is going on.
Yeah, the point is the roles are a little different. If you are at the receiving end of these bombs, then you are more likely to have a jammer, not to be victim of a jammer.
Yeah, sure.
So it's the other way around. So if you're on the throwing end of the bomb, you see that your target is beginning to jam GPS, then you should think about what you want to do. You just decide that you did this end jammers first and then throw the bombs.
Right, so what the US, if they are throwing bombs, really want to do is they want to have some reference signals in place at the receiving end.
Here's a word in the network monitoring GPS status. This is in Germany, it's called the SAMOS network, which is the state finance network that is doing differential GPS signals. The signal is being used mostly for geodesic purposes, like measuring stuff in the landscape. There's a very, very high percent in there. And you can get the integrity data of that network from the internet. So, we got 3 minutes.
Do you know how difficult it is to build such a Russian-style jammer? Is it able to do it with simple software or?
The problem is that you need at least spectrum analyzers who can see what your equipment is doing. So, which is unfortunately, pretty lucky to have a lot of equipment. And you need some experience with high frequency electronics because it's 1.5 gigahertz, which is a little bit messy to handle frequency. If you're going to the radio amateurs and ask them about would you buy me in 1.5 gigahertz transmitter, they say, yeah, you can do it, but yeah, probably you should use this part and that part. So, but my assumption is that if you get the right 2 or 3 people together, then it shouldn't be a big problem to build such a thing. So, but you need at least the radio amateurs, somebody who knows what it does in the frequency.
possible. One of the ways of actually talk about propagation. Is it possible that you make your own propagation conditions so that you can bounce your jamming signal through the atmosphere back to Earth?
What my first gehört ist ein non-nonsense signal, it's going straight with a lot of visibility. Okay. Okay, then thank you very much.